with each other what's going on. So I got interested in in questions about inference following adaptive designs, really by Vlad Dragalan. And when he was at GlaxoSmithKline, he developed a set of software called a toolkit. And he programmed up every sequential stopping rule, group sequential design, et cetera, that he could find in the literature. And he then had this randomization procedure where you could run your favorite rule, your favorite design, and he would plot the distribution of maximum likelihood estimates when the design was finished. And his goal was to show people that no matter how large you made the sample sizes, these estimates were not normally distributed. And so that piqued my interest. And some of the talks we've heard, if you listen to the talks that we've heard, like Chris, the earlier talks we heard, the adaptive design issues were they were testing problems, not estimation problems. And then there was actually a question after one of them from someone over here about estimation following adaptive design. And a large amount of work has gone into the testing problems and controlling the type 1 errors, and very little has been done or thought about with respect to what happens if you want to make a inference after, if you want to measure the effect size. You know, what is the distribution of the effect size? Well, I'm not focusing on the adaptive designs where you're doing resample calculation or early stopping. I'm looking at adaptive designs where you're changing the way in which you allocate subjects to treatments. But these are related. There are related issues in the adaptations, which I'll come back to actually in my conclusions. So this particular project actually started with a former graduate student, Ping Yao, who went to spend a summer with Val Fedorov at GlaxoSmithKline, and we tried to began honing in on a very simple problem, a toy problem, where we might get some mathematical traction to try and understand what the issues are with, in that case, adaptive optimal design. Some things I'll talk about are more general. Then Adam came along, and we came here, and Adam was in the throes of his dissertation, spent a lot of time in conversation with Val and myself and doing a lot of work and doing other things. And we were focusing then on the information, you know, how do we characterize the information that comes out of an adaptive optimal design. And then after we left the Newton Institute and went back at the final stages of his dissertation, we focused on this, still in this toy problem context, we focused on this specific case where you had 2 stages, and the first sample size is a small one. So you're not going to let everything go to infinity when you try to evaluate what's going on. So, well, that was the introduction and the background, I think, unless there's something else here. So I think most of you know, but I'll say that when we use the term adaptive optimal design, we're talking about, in the context now of a 2-stage experiment, it can be more. The first experiment is an optimal design. I'm assuming we have some nonlinear problem where the design's a function of the parameters, and so you're going to somehow estimate the parameters and do your experiment as if those parameters are true. And then at each subsequent stage, you take the data that you have, update the existing parameters, and proceed. Now, it's not hard to show, and there's several papers now that do show that in this problem, if you let your sample sizes go to infinity at each stage, your maximum likelihood estimates are going to behave as one expects them to under the standard regularity conditions. So that's not the talk of this paper. And so the motivation for thinking of this, well, there's several things. One is that often maximum likelihood estimates can take a long time to behave like normal random variables when you have nonlinear problems. But we have a specific common situation where the researchers want to take a small, typically a small sample size, get a little information, and then do something that's supposedly confirmatory. So it makes sense to think of this situation where the first stage sample size is fixed and small. So in particular, we'll do several things, but in particular, one of the results that Adam got that we'll come back to is an approximation of the distribution of the maximum likelihood estimates in this situation where the first stage is not allowed to go to infinity. And of course, we'd like the distribution of the maximum likelihood estimates. We'd like not to let anything go to infinity. So this is just, one step at getting a closer approximation than the everything is infinite one. So to say, we work with a toy problem, and so we just have this kind of typical nonlinear regression problem with additive normal errors. And so the notation is, got a point in, the notation is the subjects ni. I will just go from 1 to 2. So we've got ni subjects on each group. That's considered on each stage. That will be considered fixed. We're just going to have a one-parameter model. We're going to use one dose. Well, I'll call it doses just because most of you know that I work in dose-response situations usually, and so I just tend to think about it as dose. So at each stage, you're going to give some treatment xi, and the proportion of subjects is wi. There's the normal model. So to start with, just think of finding the second stage dose to be some function of the first stage data. So now this could be Bayesian, this could be whatever. You're just going to use the first N1 subjects, their responses, their Ys. The first the dose that they were given is considered to be fixed, so it's not random, and you're going to choose your second dose based on that. So the likelihood factors nicely. You have your vector your stage 1 responses, your vector stage 2 responses. You can break that into two components, the stage 2 data conditional on the stage 2 responses, conditional on the stage 1 responses and the stage 1 treatment, and multiplied times the density for the stage 1 responses given the stage 1 treatment. So in this case where we have the nice normal problem, that likelihood looks just exactly like the likelihood for the two independent groups of subjects. And that is true, except now this x2 is a function of all the first stage data. So, and so we have the stage 1 data and the stage 2 data both in this component. So this first component is the stage 1 data, normal random variables, it's fine. But in order for this whole density to be a member of the exponential family, this term has to be a constant. So first thing to note is just in general, this is not a member of the exponential family. And then to say, okay, well, what's it going to take to make this term a constant? Well, the sufficient statistic, if you're thinking of maximum likelihood, if you're going to say x2 is a function of the sufficient statistics in stage 1, then it's going to be a function of y bar 1. So what's it take for y bar 1 to go to a constant? Well, the stage 1 sample size has to go to infinity, or at least be bigger than like 30, right? So, well, I mean, so that gives us some sense of when this is going to behave properly. It's going to behave properly when the stage 1 sample sizes is at least of some sensible magnitude, and that magnitude will change depending on how nonlinear the nonlinear function is, but you can have in your mind the number 30. So if you have a large sample size, then everything's fine, and if you don't, well, so what? You know, what does this mean for us? So one of the standard tools that is being used in adaptive optimal design and in other procedures for inference is Fisher information. So in terms of looking at what's happening, let's just remember why we use Fisher information. So it's the variance of the score function, and we have two purposes for using Fisher information. We use it in design, we use it in inference. And the motivation is the Cramer-Rao lower bound. That is, what we're interested in is how Fisher information relates to the actual variance of the estimator that we're talking about. So let me just remind you of the lower bound formula. We have some estimate of our parameter based on n trials. It has finite expectation that is potentially biased. I'm not going to deal, well, so the formula is the variance of your estimator is greater than or equal to the squared covariance of your estimator in the score function divided by the variance of the score function. So this initial term, maximum likelihood estimates, will often be biased, but I'm not going to deal with that issue. When we think of using the Fisher information, we're thinking about having a 1 here, which asymptotically one may well have, or not. But we're thinking of a 1 here divided by the variance of the score function. So that is the inverse of Fisher's information. So Casella and Berger or somebody now has this result such that all the graduate students seem to know it, which is that this equation only will be, you can only get an equal sign here if your density is a member of the exponential family. So the first thing we notice from the slide, the previous slide, is that the equality that we have in our minds when we use Fisher's information is broken. So this is an inequality sign. So what's that mean? Well, if we're doing design, it still makes sense because you have, as your variance of the score function gets big, you're still pushing this lower, you're pushing the bound of the variance smaller and smaller and smaller, and so it makes sense to do that. If you're thinking about analysis, and you're going to develop a coverage estimate based using Fisher information, then you're going to be overly optimistic. So, I'm not sure what that says to us all, except that what we were trying to do is grapple with maybe we should be using bootstrapping or other kinds of non-parametric statistics for analyzing the data after the study is over. But at least in my hands and the hands of my students, we haven't been able to make the bootstrap work very well for these problems. So I think the inference issue for variance estimation is still is an interesting one and still quite open. Okay, so now let's look exactly at an adaptive optimal design itself. So I've got the S for the score function, break it into its little component pieces. Those of you who work with this formula will recognize this is the score function for, you know, subject J at stage I. The optimal design for stage 2, we'll put the asterisk here for optimal. And what we mean by that is we're going to maximize the variance of the score function for the second stage. That is summing over the i's here. So we have this optimal choice that we would like to make for stage 2. We have, if I use the subscript n1 here for the maximum likelihood estimate, I'm talking about the maximum likelihood based on the first stage data. And so our second stage design point is a function of that estimate. So x2 of here is the maximum likelihood of the locally optimal design point. And the design rule then is to select the second stage treatment to be the maximum likelihood estimate of the locally optimized design. So we evaluate the, well, so there it is. Okay, as simple as we could make it. Now here I just remind you that we use the Fisher's information for both design and inference and decompose the variance of the score function, the average score function, into the two variance components and the covariance component. Now, the covariance component is 0, so that causes no trouble whatsoever, and that's a general result that shows up a lot in the martingale results and other places where they look at likelihoods in this fashion. So the covariance is not an issue. The second line here is just to be specific for this particular example. The third one is to make a point. So the first term here is the variance component for the first stage data, that is the variance component for this nonlinear problem with normal errors that you would typically expect to see with a fixed sample size. So the second, this is the contribution from the second stage, and the difference is that when you calculate this variance, this expectation, it includes an expectation over the first stage data. In this case, the parameter estimate from stage 1. So it's sitting in here, it's a random variable, and the basic definition of the variance of the score function includes that expectation. Now, this is what's commonly ignored. And so, again, we're trying to evaluate what difference things make. And so we talk about this benchmark that you might make if you do kind of the best possible thing. Now, the best possible thing would be you treat everybody at the optimal design point. So that's not what we mean here. What we mean by the best thing we might do is that you started your design at some place, some dose with your first stage sample size, and that's given, and then by some magic you jump to the best place to do the rest of the data that you're going to use. So you got there, you got to the optimal design point in the second stage, and this just writes out what the information looks like here with the second stage having the optimal design point in it. And by the way it's constructed, the information in this magically arrived benchmark design is going to be better than the information in the adaptive design, A for adaptive, that was just on the previous screen. And by the Cramér-Rao lower bound, we can bracket these things now. So we have the, quote, the best thing, so again, what we're interested in is the variance of the parameter estimate. And that's going to be bigger than, so the variance from the adaptive design will be an underestimate of that, and the variance, assuming the optimal design point, is going to be even more of an underestimate of it. So, so the question is, can we do anything to improve on things? And I just remind you that if you take both sample sizes and go to infinity, then, and we use this same notation we had on the previous slide, that the maximum likelihood estimate is going to converge to a normal with the inverse of the information matrix at this optimal design point being being the variance. So what happens if we don't let n1 go to infinity? Then if we were to use this adaptive design, the information with the adaptive design point in it, it would be a better approximation, as we've just shown by the Cramér-Rao bound. And we'll say more about this in a moment, but I want to bring in the one option you have, which is to do, when you go to your second design, you throw all the stage 1 data away. In this context, that's the same as, quote, conditioning on the design, because the design for stage 2 involves all the stage 1 data. So if you say you're going to condition on the design, and that includes the design point for stage 2, it means you're going to condition on everything from stage 1, including the responses. So,
may I ask a question to the first slide?
Yeah.
N1 is converging much faster to infinity than it is. So what is the ratio between N1 and N2? There must be something.
There must be. Forgive me.
And even if N1 is of the same order as N2, I don't agree that the first line is correct.
You don't? Well.
No. I mean,
you cannot divide by square root of divide or multiply by square root of n. Assume that n1 is going to infinity as a log.
Yeah, that's
n1.
No, I understand your point. I'm sorry I missed it. They obviously have to be related to each other. I was just sloppy in putting up the slide, and I will fix that. But yes, they do have to go. I mean, they can't just go at any rates and it work. I agree. So I take that correction. But if you throw away the first stage data, the maximum likelihood estimate has poor performance. And we saw that in lots of simulations, so we kind of gave up looking at it. At the time that Adam was looking at that, I was thinking of just this fact that you were going to go to stage 2 and throw all the data away. I wasn't really trying to digest this conditioning argument that the throwing the data away was the same as making the conditioning argument. So conditioning is an important issue, and I don't come back to that here. So what Adam got was this result, which is if you let n2 go to infinity and you have n1 fixed, then the limiting distribution is the product of two random variables. And one of those random variables is normal, which is what we would like to have and expect. And the other one is this function of x2, which is then a function of y bar 1, which is what makes it random. So if this were a constant, then this u would just slip right into the variance component of the normal distribution. But it's not constant, so it sits out here in front. What we can So it's a scale, it can be called a scale mixture of normal random variables, or for those people that are very comfortable about sticking parameters in your model that are random variables, then it's a hierarchical model. So this is a natural, so getting this, I think this is a different way of constructing hierarchical models than what one normally thinks of when one talks about hierarchical models. One thing that's interesting about this formulation is that this random variable u provides a measure of the cost of using stages. And that needs a little bit more exploration. But certainly if u were just like 1, then, or if u were just this constant, so it goes into the variance function, you'd have the variation that is the case when you don't have stages. But this extra variability, you know, you're going to have more variability or less variability. It's the price you're going to pay for using the stages. As I say, I haven't thought that idea of using u as a measure of cost out, but it seems to me that it's sitting there for that purpose. So here's a specific example. We've got the exponential mean function, and we can write out for this particular function what the benchmark information is and what the adaptive design information is. And a couple of comments about this one is that the maximum likelihood estimates are only are bounded, and so this pi a and pi b are the probabilities that you're actually going to hit the bound. And if you are talking about finite samples, then these probabilities can be substantial, and your measure of information is going to change a lot if you sort of pretend like you're in the middle and you don't have any probability of hitting the bounds. So this is the information for this problem. Adam got the distribution of u, and the whole distribution of the product between u and q can be evaluated numerically for this problem. So these are some cumulative distribution functions. Using, I think he said it was 10,000 or 100,000 or some large number of simulations. He evaluated the actual distribution of the maximum likelihood estimate, and so the black curve, which is running through here, is considered like the truth. The red curve is the distribution based on assuming that you have gone to the optimal point. So this is what's commonly used. So the thing to note about the red, here we have n equals 30, here we have n equals 1,000. So if you're looking at the difference between the red and the black, well, it looks somewhat different on the right-hand side than the left-hand side, but if you look here, you don't see it getting any better. If you look here, you actually, maybe it's getting worse in terms of distance. Using the adaptive design, at least the blue gets closer to the black, and then things are better using the product of u times q. Now, I'll show some more quantitative information there, because that's hard to see. Okay, so one doesn't want to pay attention to all the numbers here, but just the colors. So we have three different values of the parameter. We have total sample sizes that vary from 50 to 400, thinking 400 is large. We have the first stage sample size going from very small to staying small. And then we have the integrated difference between the CDF from each of these three approximations and the true one. And so small is better, and small is bolded, and the cumulative distribution, the UQ, in every case is smallest, except when we get a big parameter and we get reasonably large sample sizes down here, we get a couple of exceptions. And so wanted to look at it with some really large sample sizes, like n equals 400 and n equals 100. So now we're in the large sample size realm. We have the sample size for the first stage starting out really small, but also getting pretty big. So you might consider these to be asymptotic value or close to asymptotic values. And we compare the adaptive optimal design and the U times Q design, and it takes the stage 1 design to be up to 200 before the adaptive optimal starts to look better than the UQ approximation. So one thing that was all done with a fixed stage 1 sample size. One thing that came out of this investigation, or one question that arose, of course, is how do you pick stage 1? And I think it's Luke Presanto that got a result recently that said stage 1 should be of the order square root of n. But order square root of n still leaves a lot of leeway in terms of what exactly should it be. And we determined that equal to the square root of n is not, in the situations we looked at, not the best answer. So we introduced this notion of locally optimal sample size, where you have your information based on the adaptive design, and this is W1, the proportion you're going to put on stage 1, and you can plot the information based on your sample size. And if you knew the parameters, you could pick off the maximum. It's at least in this case, it's a nice, well-behaved function. And so what Adam ended up proposing was in order to select a stage 1, if you have the luxury to do so, a stage 1 sample size is to put a prior on the parameters and get a to sort of average over these options and choose your first stage sample size. Now, normally your first stage sample size, you won't have that kind of freedom. It's going to be based on logistics and at least be highly restricted to be, say, small. But by doing this sort of analysis, you can see what kind of price you're paying in terms of efficiency. So this is the recommendation. Well, this is the definition of the locally optimal first stage sample size. It maximizes the information. Here's some examples where you have different values of theta, different total sample sizes. How many should you put on stage 1? Here you should just do one stage, and in the other cases it varies considerably. So it's one more thing to think about.
Nancy,
Yes.
I have a question. So concerning this table, so it looks like numbers in this table should depend on, first of all, a true value of a known parameter. It's obvious. You probably
Yeah, I'm using the same parameters for this whole.
The second, it should depend upon your initial guess, because to construct initial design and continue, you still need some guess.
Yes, right.
And if you guess, let's assume true parameter, then obviously design, which start with 0 and 1, will be the best.
Yeah, there's a.
You will start from 0. On your plot, the curves start from 0 information. Why misunderstood?
Wait, where are you talking about? Here?
Yeah, right here. If I knew truth,
This is about 15 points.
no, but still, if I started my second stage with design which is locally optimal for true parameter, it should be the best design.
In terms of stage one, yeah. I mean, in terms of the...
In sense of any stage, and if my stage one is 0, because if I start at stage 1, it gives me estimator which will be worse than true value.
Well, that could definitely happen. I mean, okay, I don't have that picture with me, but if you're looking at when do you increase information by having a two-stage design? There's definitely a point, there's definitely a window around the optimal design point at which you are better off doing a stage 1 design. I don't think this conflicts with that. I mean, you're varying different things. So
this probably you have to define a little bit more accurately how you proceed. So
okay, well, there were a lot of tables, and we're picking out a few, but that is certainly a fact that if you start your design very close to the truth, you're better off not to have done two-stage design.
It's the other way around.
If you start close to the truth, you're better to have just done a one-stage design.
One-stage design without stage N1.
Well, then N1 is equal to N. If you do a one-stage design, N1 is equal to N. Okay, anyway.
Okay, we can accept it.
So yes, I couldn't do everything here, sorry. Which way am I going? We're almost over. So we have our optimal design. So I want to just make some comments in summarizing. So we have these words that are thrown around about designs, like the design being ancillary, which I think, at least for a long time, sort of meant, well, that, oh, you can forget it then, whether this be a Bayesian design or a frequentist design. But designs can be ancillary and still not independent, and even though the likelihood will factor, and it's going to look just like a likelihood you'd get as if your design was fixed, when you go to look at the variance, things are more complicated. Also, that if you're going to condition on the design, I mean, conditioning is a big concept in statistics, but in this kinds of situations, if you say you're going to condition on the design, you're talking about conditioning on responses from prior stages, and is that what one really wants to do? And so the whole concept of conditioning on a design is different. In the case of this two-stage design, in which the first stage sample size is fixed, we found, there's this taking the inverse of the variance of the score function is an improvement over dropping that expectation over the first stage data. So then we looked at approximations of the variance of the maximum likelihood estimates, and one really interesting result was to get this scale mixture of normal random variables. And I want to point out that this is the same result that's obtained in quite a few other situations. In particular, the birth and death urn of Ivanova et al. Had exactly this kind of distribution. The randomized reinforcement urns within the contexts and qualifications with which they were examined have this kind of distribution. And these are really different in that for the situation that we're talking about here, the randomness comes in how you're choosing your second stage design point. In those urn models, the randomness in the scale mixture comes from the fact that you have your sample sizes on each treatment are random, even though you have a fixed total sample size. And then Sergei Terima at the Medical College of Wisconsin has been doing work on, in the situations more like we were hearing this morning, where you're talking about interim analysis and recalculation of sample size, And he's looking at the maximum likelihood estimates after those kinds of adjustments, and also coming up with a scale mixture of normal distributions for the maximum likelihood estimates. So this seems to be a fairly standard result that's showing up repeatedly in many situations. And so I'll just note that it's not true for like all response adaptive designs, however, that if you, for example, use random walk rules, which have the Markov chain properties, these up and down designs, the sample size proportions go to constants, and therefore all the standard asymptotic normality goes right through. We suggested the idea of locally optimal sample sizes, and that's it. Thank you.
So it's time for further questions. Yeah.
So what do you really mean by ancillarity there? Because the sufficient statistics are different, right? The set of sufficient statistics in a two-stage design are different than in a fixed design. So, I mean, I guess what you're saying is the likelihoods look exactly the same, but they're not the same.
But the parameters separate.
Yeah, but they don't look the same. I mean, they're the same, but the set of sufficient statistics is completely different.
That's true. That's true. I'm mainly referring to the fact that it's been declared that...
And now you have the sample size that actually depends on the theta parameter, right? So it's...
Well, if you go to that next step, yes. What we looked at here, the sample size was fixed.
Yeah. How to understand what the objective is again? You're talking about the variance of your estimate overall, and that's something you'd like to be small. But you might also use that estimate in, say, making a confidence interval for something. And it's in that I still wonder whether one ought to be interested in something more conditional. You know if you, in a very different setting, if you take a few observations and then you toss a coin and either take another 50 or another 1,000, you'd expect to condition your inference on that toss of the coin.
So you're arguing for throwing the first stage data away?
No. But well, not necessarily. But what I was wondering, in your mixture distribution with the U, by the time you finish a study where the second stage was large, can you say more about what value U has taken? And in which case, that might be something you could...
So what was the if part, if you finish the study?
So if you have in a sort of asymptotic sense, a small first stage and then a large second stage. And you've got your mixture distribution with U times Q. You must know a lot about, if you like, the value that U has taken this time, is what I'm thinking.
Well, you'll have a number for it.
And hence you could take a variance which is conditioning on that value of U, maybe?
Maybe.
Inferences?
Yeah.
I wonder if is that an in-between between throwing away the first stage data and
yeah, I guess, I mean, so the question's sort of out there. Well, now you got this result, so what? And how do you use it? And
it reminds me of something with Stein's two-stage procedure where you estimate a variance and then change things. And some very funny things happen there if you try and do conditional inference. I'll have to try and remember what they were. I'm very happy to talk about them later.
Yeah, no, let's, I mean, if you could, yeah, let's talk about it more because that's sort of where we are.
Sorry, I have to interrupt at this point.